Hello, I'm Maximilian. This is Tell Me Something Interesting. Today's topic, the James Webb Telescope. This topic is very vast. The Webb Telescope covers many different areas in astronomy. The effects it will have will be massive in our search to understand the universe. So this video series will be multifaceted and try to cover different ways it will shine a light into areas that's hard to see and others that are quite literally invisible. So to start, what is the James Webb Telescope? Well, what is a telescope? A telescope is a device that uses lenses, curved mirrors, or some kind of combination of both to see distant objects. Typically, when we think about telescopes, we think about long tubes with a glass at the end. We use these to look out to the stars with very little definition. Something that would have been the height of scientific advancement 100 years ago can be had for less than $10 now. But the Webb telescope isn't anything like these. But what about the meteor telescopes, the ones that have been giving us images like these? How is the James Webb different? Unlike what we see in the traditional telescopes that look out into the stars using the visible spectrum, the Webb will view the universe through infrared. What does that mean, infrared? Visible spectrum. Well, light is a spectrum. What we call visible light is just one aspect or one piece of that spectrum. Imagine you have 7 boxes sitting in front of you, each marked differently. One says radio waves, then microwaves, infrared, visible light, ultraviolet, X-rays, then gamma rays. These are all aspects of the spectrum. Now, we as humans can see everything that's inside the box marked visible light. That's the light that's visible to us. But we can't comprehend the contents of any of the other boxes with our own eyes. We simply can't see it. It's as if there's a lid on these other boxes. But with different technologies, we can interpret what is inside the other boxes, or take the lid off and see what's inside. So the James Webb Telescope will be able to look at everything that's inside the infrared box. But what might be in there? So light, as it travels through space, has a tendency to redshift, sometimes even blue shift. To keep it simple, photon waves can change boxes as it travels. The wavelengths can either grow longer or shorter, and the length of that wavelength is what designates its location on the light spectrum. So how do we illustrate this? Well, we've all heard of Starbucks and their crazy drink sizes. They have the demi, the short, the tall, the grande, the venti, the trenta. If you walk into Starbucks and you order a demi macchiato, it will always come in a demi cup. If you order a short chai tea, it will always come in a short cup. The name of the cup signifies the size you will receive. Whether that will be very, very small, small, medium, large, or extra large. By saying the size you want, you signify the size you will get. Light is signified by its wavelengths. The wavelength of radio waves range from 30 centimeters to thousands of meters. The wavelengths of microwaves extend from 1 millimeter to 30 centimeters. The wavelengths of infrared, what we're discussing now, range between 1 millimeter to 780 nanometers. So in Starbucks, there's no venti coffee. There's just coffee in a venti cup. The same coffee you can get in a short cup or a grande cup. And there aren't any visible light photons. There's just photons whose wavelengths make them visible, and if the wavelength changes, so does its position on the spectrum. So back to the boxes. Something that starts in the box marked visible light can travel into any of the other boxes. Over the billions of years that light has been traveling within the universe, over vast distances, while space has been expanding or stretching, that means light within it stretches, shifting that light's wavelength to longer wavelengths. This can make distant objects very dim or invisible at visible wavelengths. Redshift means that the lights emanated by these first stars and galaxies, as visible or ultraviolet light, actually gets shifted to a redder or into a longer wavelength by the time we see it here. For very high redshifts, that visible light is generally shifted into the near and mid-infrared part of the light spectrum. For that reason, to see the first stars and galaxies of our universe, we need a powerful near and mid-infrared telescope, which is exactly what the James Webb Telescope is. So what is so special about the James Webb Telescope that makes it so it can look into the infrared? Well, first, it looks different. I mean, really, really different. When you think about telescopes, this isn't what comes to your mind. I mean, it doesn't really fit into anything that we typically assume a telescope would look like. Even the Hubble looks different than the James Webb. But this difference has a purpose. So first, the sun shield. Infrared radiation is heat. Because the James Webb peers and sees in infrared, any heat source can interfere with the accuracy of the instruments. Think about the Parkes Observatory in Australia. They were picking up radio waves starting way back. Way back? Oh, wow. Man, time flies. Way back in 1998. But they had no clue where it was coming from. 17 years later, the mystery of the radio waves being picked up was found out to be the microwave in the kitchen. That's called interference. And the Webb's microwave could be any amount of heat. So to observe in the infrared, it must be kept at 50 Kelvin, or negative 223 degrees Celsius, or negative 369 degrees Fahrenheit. So what must be taken into account is the sun, the earth, which can reflect the sun's light and also block the telescope, and our own moon, which also can reflect the sun's light and block the telescope, and some of its own instruments. So the sun shield helps to deal with these issues. The telescope will be positioned so that the sun, the earth, and the moon are all on the opposite side of the telescope's instruments, which creates the conditions necessary for it to be used. Next, we have the mirror. What we have to keep in mind is that this telescope needs to be launched from Earth. So its ability to fit in a spacecraft is very important. So that is why we see the hexagonal segments designed for the mirror. This is foldable, which is very necessary. The design of the mirror is a 3-mirror anti-stigmat, which helps to eliminate optical abrasion. So the goal is to get the sharpest and clearest images possible. This 3-mirror design will ensure that we do. The Integrated Science Instrument Module, the ISIM. Now this is the heart of the James Webb. It holds and runs the modules that make everything possible. It provides electrical power, computing resources, cooling capability, as well as structural stability. It also holds the 4 science instruments and the guide cameras for the Webb. We have the NIRCam, NIRSpec, MIRI, FGS, and NIRIS. All acronyms, but this video will be long enough. The NIRCam has 2 major parts. It's an imager from 0.6 to 5 micron wavelength. Now, earlier I mentioned light as a spectrum. And the way we define where each light falls within the spectrum is by its wavelength. The longer the wavelength we get radio, the shorter we get gamma. Everything else falls in between. And the NIRCam is looking at the wavelengths of infrared. So besides the imager, the NIRCam has a sensor to keep the 18-section mirrors functioning as one unit. In other words, it's a camera that's looking at infrared, but also has the ability to make sure all the mirror segments work together. The NIRSpec instrument is a multi-object spectrograph. Now, what is a spectrograph? Well, a spectrograph is an instrument that separates incoming light by its wavelengths or frequencies. I know, this seems very mundane. I mean, we can buy a prism today and get it tomorrow. And prisms do something very similar. But there's something very interesting about light. Light carries information about its journey with it. The light reflected from iron is different than the light reflected from carbon. Now you'll say, of course, you can look at iron and you can tell it looks different from carbon. Carbon? Carbon? Carbon monoxide, carbon footprint, coal. Carbon is coal. Carbon is coal. You can look at iron and tell it looks different than coal. But what if they weren't in the visible spectrum? How would you tell? You wouldn't. I wouldn't. I mean, it's not visible. But the photons would still have that information. And if we could view the photons, we can gain an understanding from things millions upon millions of miles away. And the spectrograph will be able to do just that. So with the spectrograph, the Webb will be able to see the makeup of different galaxies we've never even seen before. The MIRI, or mid-infrared instrument, is a camera and a spectrograph that observe in the mid to long infrared radiation from 5 to 28 microns, as well as a chronograph. But why does this matter? Well, imagine you see a giant dust cloud in space. Wrong ball of dust. You want to see inside of it, but well, the dust. Do we wait for it to clear? Well, no, we can't. But we also can't see much because visible light does not escape. But light does escape. And that light that does escape, MIRI's cameras will be able to pick it up and see, as it were, behind the curtain of dust. But why would we want to do that? Well, the early stages of star formation and planets are often hidden behind these dust clouds. And the MIRI also has a new technique for its chromograph. It's very technical. It's called a sun visor. Actually, it's a masking technique, but the concept is the same. The masking shades the glare of celestial bodies, enabling the camera to see other planets that may be orbiting these stars. Whereas most of the other instruments on the Webb can see from the start to near infrared, or even as short as orange visible light, the MIRI can see longer wavelengths of light. The Fine Guidance Sensor, the FGS, allows Webb to point precisely so that it can get high quality images, like, a guidance sensor would. The Near Infrared Imager and Slitless Spectrograph. NIRIS will be used for first light detection, exoplanet detection, and exoplanet transit spectroscopy. Or use the rays of light from the system star as the exoplanet passes in front of it so we can capture those photons and begin to look at and see what kind of conditions are on that planet. So those are the instruments and the Webb, but it still has to get to its position. Now, unlike most telescopes, the Webb will not have a semi-close orbit around the Earth. After launching and once in space, it will begin the most worrisome part of this whole thing. The sun shield will expand. There are many parts to the sun shield. Any part not functioning can doom the mission. And then the mirrors must unfold. Now tell me if you heard this before. There are many parts to the mirrors, and any part not functioning can doom the mission. The Webb has a 1,000,000-mile trip to reach its destination, where it can orbit the sun in line with the Earth. This orbit allows one side of Webb's sun shield to always face the sun, the Earth, and the moon, blocking their heat and light from reaching the telescope's heat-sensitive instruments. Webb's month-long journey will take it to the second Lagrange point, L2, one of 5 positions in space where the gravitational pull of the sun and Earth balances the centrifugal forces required for a spacecraft to move with them. This makes Lagrange points particularly useful for reducing the fuel required for spacecraft to remain in position. The location also enables continuous communication with Webb through the Deep Space Network. As Webb is orbiting L2, it is also moving around the sun. Given that the Webb can only point to roughly half the sky at any given moment because it can't look in the direction of the Earth and the sun, this affords the Webb access to the entire sky over the course of a year. So that's the Webb, basically but not basic. I mean, this is technically rocket science, so it's tough to explain something that's so much more vast than the time you have required for it. Am I leaving anything important out? I hope not. Like I said in the beginning of this video, this is a soft introduction. So as we fade into the back, let us look at the accomplishments so far in the hopes of so much more to come. And I gotta tell you, this is incredibly interesting.